Cutting tools ideal. What properties would be ideal for a good cutting tool? High hardness at high operating temperatures. Lowest friction to minimize heating of the tool by chip friction. No chemical reactivity with workpiece to prevent reactions and adhesion. Toughness to resist impact loads such as those in milling. Stiffness and strength to minimize deflection and support greater cutting loads. Low cost. Cutting tool properties. The properties are hot hardness. Retaining hardness at high temperatures allows higher cutting speeds. Toughness allows for interrupted cuts due to fracture resistance. Low friction leads to lower heat generation. No chemical reactivity leads to no sticking, built-up edge, adhesive wear. Stiffness leads to less deflection, leads to better accuracy. Strength leads to higher loads, more demanding applications. Higher thermal conductivity leads to better heat dissipation. Low thermal expansion leads to better dimensional accuracy. And low cost would also be desired. Cutting tool materials. There is no ideal material. Cutting tool development has been an evolution, first with base materials, then with inserts, and currently with coatings. Cutting-edge technology, no pun intended, is a combination of holders and supports, inserts that are often composite, and coatings. Materials will be covered in a historical timeline as this makes more sense. Machining time reduction. The quest for better tool materials is due to a desire for greater machining productivity. Machining time for the same part in the figure has dropped dramatically due to the ability of tool materials. First, high carbon steel was used, but it would take 100 minutes. Then the advent of high-speed steel, called that because it could be run 3 to 4 times faster with the same tool wear, dropped the time to 26 minutes, or about 1/4. Then cobalt alloys, cemented carbides for 1/15 of the machining time. Advances in carbides cut that in half, coatings cut that in half again, and multiple coatings cut it in half again. The result being that by about 1985, machining speed was 142 times faster than in 1900. Tool material introduction timeline. In this figure it can be seen the different times at which different types of tools were introduced. Comparative hardness of cutting tools. Hot hardness is the ability for a material to remain hard as temperature increases. Note that hot hardness increases from carbon steels to high-speed steels to cobalt alloys to carbides to ceramics. Another issue with temperature is the fact that upon cooling, some tools regain their hardness and some lose it. Carbon steels and high-speed steels lose their temper, changing their microstructure and thus becoming permanently damaged. That is another reason not to overheat these tools during sharpening. Cobalt, carbides, and ceramics do not change internally, so they fully recover. Question: so why not just use ceramic tools and forget the rest? Hot hardness versus toughness. In this schematic it can be seen that materials that possess good toughness tend to have less hot hardness and vice versa. Thus, applications such as milling that have continuous impact on the cutting tool with the workpiece require toughness, and thus carbides and high-speed steels dominate this application. Continuous turning, on the other hand, requires very little impact resistance, and the harder grades of material can be used. Note that other applications such as drilling don't have impact loading, but the shank needs to be able to withstand the shear stresses of the operation. The ideal material would be in the top right corner of this diagram and would also be cheap. Reasons: toughness versus strength as described, lot size versus cost. In some instances, a more expensive tool can be purchased, but if the production run is only a few pieces, the benefits do not translate on a cost per piece basis. Shape: some of the materials can be easily produced in the desired shape of the cutter. Tool properties versus machining conditions. The figure shows how the material properties relate to the cutting conditions such as speed, but also depth of cut, feed, and interrupted cuts. Material removal cutting tools. Carbon steels. They're high carbon steels, but they are no longer used. High-speed steels allow for 3 to 4 times the speed of carbon steels. Molybdenum and tungsten-based. Molybdenum is more widely used due to the lower cost. They're still used extensively, particularly in applications such as drills, taps, etc. Cast cobalt is better than high-speed steel, but largely has been replaced by carbides due to the higher toughness that they have. Compositions of high-speed steels. Some sample compositions of high-speed steels. Note the high levels of carbon and high levels of molybdenum and tungsten. The basic principle is that the carbon and the other alloying elements form very hard carbide particles that resist wear in the tool. Also, they have a steel matrix which makes them very tough. Carbides. Powder metal produce tungsten carbide for hardness and wear resistance and a cobalt matrix for toughness. In essence, the same idea of high-speed steels, but with better and more controlled materials. Titanium and tantalum carbides are also used to supplement tungsten carbide as they have better properties. Titanium carbide is also used exclusively as a carbide for some tools known as cermets. Carbide microstructures. In this figure, microstructures of straight tungsten carbide cobalt alloys are shown. In figure A, 97% tungsten carbide, 3% cobalt alloy, medium grain size of the carbide. In figure B, 94% tungsten carbide, 6% cobalt alloy, medium grain sized tungsten carbide. In figure C, 94% tungsten carbide, 6% cobalt alloy, coarse grain of tungsten carbide. In figure D, 85% tungsten carbide, 15% cobalt alloy, coarse grain of the tungsten carbide. The carbide particles are what resist wear in the cutting tool. The properties of the carbide will change with changes in the grain size of the carbide particle and also with changes in the ratio of cobalt to tungsten carbide. More cobalt makes the carbide tougher but less hot resistant. Insert tooling. Carbides are not typically used as complete solid tools. Generally, they are used as disposable inserts that are placed in a stiff steel tool holder. In this manner, the tool tip, the part that actually cuts the material, supports the hot conditions, and the support provides structural stiffness and strength. Another advantage is that once the inserts are worn, they can be indexed or rotated in the support to provide a fresh cutting edge. In most instances, the insert can be flipped to present several new cutting edges. Carbide inserts. Note that the typical carbide inserts with various shapes and chip breaker features. Round inserts are also available. The holes in the inserts are standardized for interchangeability. Carbide inserts 2. A schematic of carbide inserts with chip breakers. Example support for insert. One method to hold an insert. In this case, a chip breaker is also used. This is only one of many methods of holding inserts on tool holders. Insert holders and pockets. Insert holders are made for specific operations and of specific geometries. The holders also have pockets in them that provide a snug and accurate location for the insert to sit in. In this manner, insert changing becomes a very easy and fast task. Other examples of insert tooling. On the left figure, there are metal cutting drills with indexable carbide inserts. This has the added advantage of being able to use a tough and strong shank material, steel, that will be able to withstand shear forces and impacts. In addition, forming steel to the desired shape is much easier than for carbide. On the right figure, end mills with indexable carbide inserts. Cutting tools, ceramic and diamond. Ceramic tools. 99% of ceramic tools are alumina or aluminum oxide. They are harder but more brittle than carbides. Single crystal diamond is the hardest material. However, the cut must not be in the weak cleavage plane of the diamond because it will break easily. Diamond tools experience very little wear, which leads to very accurate cuts. Polycrystalline diamond is less orientation sensitive than single crystal diamond and is also cheaper. Diamond is not used for ferrous metals due to the chemical affinity and the high machining temperatures which convert the diamond to graphite and tend to oxidize or burn the carbon in the diamond. Cubic boron nitride. CBN or cubic boron nitride is used for very hard materials on the order of Rockwell C of 60. It has a high tool cost, but it may be worth it. An economic analysis should be performed when these tools are considered. Cubic boron nitride inserts. Construction of a polycrystalline cubic boron nitride or a diamond layer on a tungsten carbide insert. This insert on an insert is common with the more expensive materials. Another reason is that by having a small piece of the CBN backed up by carbide, the overall performance of the CBN is increased toughness, but with little cost in terms of hot hardness performance. Cubic boron nitride insert examples. Inserts with polycrystalline cubic boron nitride tips in the top row and solid polycrystalline CBN inserts in the bottom row. Applications for cubic boron nitride. Typical applications of CBN tools. Use of CBN inserts in hardened steels from 55 to 62 HRC, which is very hard. In Figure A, facing, Figure B, copy turning, Figure C, threading, Figure D, grooving. Note that all these operations are continuous and do not have impact characteristics to them. Tool coatings. Coatings have been developed to enhance the performance of cutting tools. Some examples include titanium nitride, which is used for low friction, alumina or aluminum oxide for chemical stability and wear resistance, titanium carbonitride, which is also known as titanium nitride, is used for strength and wear resistance. Coatings are more commonly associated with carbide tools, but high-speed steel tools and ceramic tools are also coated. Coatings are applied to all types of tools, inserts, drills, etc. Coated tool example. This figure shows a 3-layer coating on a carbide substrate. Coatings can be single layer, multiple layer, and in some instances repeating layers. Multiphase coatings, another example. Multiphase coatings on a tungsten carbide substrate. 3 alternating layers of aluminum oxide are separated by very thin layers of titanium nitride. Inserts with as many as 13 layers of coatings have been made. Coating thicknesses are typically in the range of 2 to 10 micrometers. Comparative properties for cutting tools. Various properties for various different types of cutting tool materials. Edge strength versus tool angle. Relative edge strength and tendency for chipping and breaking of inserts with various shapes. Strength refers to the cutting edge shown by the included angles. The larger included angles provide more resistance to tip breakage. This is particularly important for brittle materials such as ceramics. Edge strength versus edge preparation. Edge preparation of inserts to improve edge strength. Geometry in a single point cutting tool, isometric. The various angles in a cutting tool. The side rake angle is what would be considered the cutting angle of the tool. Note that in this type of tool, the cutting is done by the side and the nose radius. All of the other angles are clearance angles, so the workpiece will not rub against the tool. The actual angles are those of the tool as it is presented to the workpiece. So if the tool is not straight, the angles presented to the workpiece will be different. Cutting tools for other machining processes will also have a rake angle, that is, the cutting angle, and various types of clearance angles. Geometry in a single point cutting tool, orthogonal views. Another view of the cutting tool, this time a multi-view view. Comparison of approximate cost of selected cutting tools. Various types of cutting tools with approximate prices. Note the increasing cost trend towards the more modern tools. It is important to note that tools shouldn't be selected on price alone, but rather under productive value. Performance comparison of coated and uncoated carbides. On this table, it is possible to see the changes in terms of production and productivity between coated and uncoated carbide tools. For example, let's look at the next to last example, the turning of cast iron. Parts produced per cutting edge is 17 for the coated tool versus 7 for the uncoated tool. From that alone, the coated carbide should be able to cost 242% more than the uncoated carbide. Looking at the metal removal rate, the coated carbide will remove 20 cubic inches per minute, while the uncoated carbide will only remove 10, so twice as much. This increase in productivity would also save production costs. Thus, even though it is initially more expensive, about 20 to 50%, it is worth more than 250% more. Economic analysis of tool materials. When comparing tool material costs, it is necessary to include all the costs that are affected by the change in tool material. In this case, the change to a cubic boron nitride tool from ceramic one has a high price tag, about 15 times more. However, when other factors are included, it can be seen that it is quite competitive. Another question is whether the cutting speed is higher, thus making the tool more productive as well. Economic analysis of tool materials 2. Another example. Here the machining cost per piece, which includes the cost of running the machine, is included, and it can be seen that the most expensive insert produces the lowest cost. Determination of cutting tool and process parameters. The constraints indicated on the top, left, and bottom side determine the outputs. Some constraints include workpiece material, geometry, finishing versus roughing cuts, machine capabilities, etc. The outputs are tool material selection, cutting speed, feed, depth of cut, and cutting fluids used.